All right, today we're going to cover lesson 2.2, which is a little short lesson looking into power functions. So power functions are functions that are written in a certain form where k is a number that is a coefficient multiplied by a value x that is being raised to a power. And the difference between a power function and a polynomial function, like from last section, is that a power function can have any kind of exponent you want. It can have a fractional exponent, it can have a negative exponent. It just can't have a zero exponent, okay? In a power function, the coefficient value at the beginning is called k, and that has a special name specifically for the power functions, and it is called the constant of variation, okay? So make sure you understand the constant of variation is just referring to the coefficient in front of your power function. Power functions can be set up in one of two ways. In option one, they could be set up proportionally or directly. So if a power function varies directly, that means that the function will have multiplication as far as the constant of variation and the variable x go. So like I'll give you something that you know. Circumference equals 2 pi r. That would be a power function with a direct variation because the 2 pi, which is your coefficient, is multiplying the r, and so that makes it a direct variation. So indirect variation is when you have a power function whose constant of variation and variable are divided. So let's say something like, I don't know, the base of a rectangle is equal to the area divided by the height. So height would be like your variable, area would be a constant value, and they're divided, which makes it inversely proportional. Here's a couple examples of formulas that you know from geometry and science. So these are all power functions. They all do have a constant of variation, and they all have a variable that contains an exponent. So if I ask for the power of this first power function, you would just tell me the exponent tied to your variable. So in that case, it's just 1. The constant of variation is the numerical value tied to your letter, or also known as a coefficient. For the area of a circle, the power for that is 2, and the constant of variation is pi. In your force of gravity formula, k is your constant of variation, and the power in this case is 2. It appears to be 2. However, this is written as a fraction. So it's important to recall from Algebra 2 that you could also write this as k times d to the negative second power, because negative exponents mean to turn that thing into a fraction. So when I give the power here, the power would actually be negative 2. Same thing for Boyle's law down here at the end. This would be written as k times p to the negative 1 power. So the power is negative 1, and k is your constant of variation. Example 1, in the formula, state the power and the constant of variation. So just one more. The power is going to be whatever's tied to your variable, in this case t, so power is 2. And your constant of variation is going to be 1/2 and g. And it's not stated very clearly, but g is equal to the gravitational pull. And that, hopefully you remember from science, that gravitational pull is the same for no matter how big or small the object is. Okay. So for this one, so state the power and constant of variation for the function, graph it, and analyze it. So this one, I'm not going to do graphing because we're going to address this graphing question here in a moment. But it is good to look at this question because we haven't had one with a radical yet. So the constant of variation is 2 because it's the number in front. However, I think I'm going to ask you for the power to think of another way to write the square root or cube root or fourth root in this case as an exponent. So anytime you have a radical, you can rewrite it as an exponent. And in this case, because it's the fourth root, this exponent would be equivalent to 1/4. So like the square root of x is equal to x to the 1/2 power. The fourth root would be x to the 1/4 power. So you've got x to the 1/4 power. Clean this up a little bit. So this expression that I just wrote is equivalent to what we started with. So I'm going to write it this way. That way I can very easily identify my power as 1/4 and the constant of variation as 2. Okay, so something very similar to a power function, but a little bit more specific, is a monomial function. So monomial function is like a polynomial that only has one term. Because mono means one. It kind of does look like a power function, and I guess it is. It's just a more detailed kind. So in a monomial function, you will still have the constant of variation called k, but we're being more specific with monomial functions in that we want a to be a positive integer, meaning a positive number that is also a counting number, aka not a fraction or a decimal. All right, so we're going to look at power functions and kind of analyze their graphs on this slide. So here is your setup for power functions. And I'm going to ask you different scenarios. So what would the graph look like if the value of a, which is the exponent, is larger than 1? Let's make an example here. So we could have a function that looks like x squared. That does have a power greater than 1, or x to the third, or we could even, make it 2x squared, something like that. But this is what my power function would look like if the exponent was larger than 1. What would that look like if I wanted to make a graph of it? Okay, but we're going to do something interesting. We're just going to look at the first quadrant of the graph. So x squared, is a parabola, which is a U shape. X to the third is kind of like an S curve, if you will. But in the first quadrant, they both kind of look like each other. They both sort of have that little curve look to them. So just in the first quadrant, both x squared and x cubed would resemble this general shape. Okay, let's keep going. What if in this setup, what if a was exactly 1? Well, if a was exactly 1, that means that you would have a function that's similar to the identity function. And hopefully you remember what the identity function looks like. It is a straight line going right through the origin, something like this. Okay, what if a was a number between 0 and 1? So that to me is like, maybe 1/2 or 1/3 or something like that. So what would that graph look like? Well, x to the 1/2 power is the same as square root of x. X to the 1/2 power, or 1/3 power, is equal to cube root of x. So graphically, we can compare the two. We're just going to look at, again, in the upper right-hand corner, quadrant 1. Square root of x, starts at the origin and kind of just goes at an angle like this. Cube root of x actually looks similar, but it just continues in both directions, kind of like the cubic function. Okay, what if a is smaller than 0? Well, if a is smaller than 0, that means that you would have a negative. So it could be -1, -2, something like that, which is the same as 1 over x or 1 over x squared. Okay, again, let's kind of zoom in and look at the first quadrant. If I were to graph 1 over x, it would be just the top right corner of the reciprocal function. 1 over x squared is the same thing, except it would have like a matching part on the other side. So we're doing this because I want to point out that power functions, even though the exponents change, we can group them into similar categories, and their graphs look similar for the things that are in that category. So here on the next slide, we have kind of a view of all of those different situations kind of compiled into one graph. So it's just about understanding functions and their behavior. Okay, so if you have a power function and you know that the exponent is a negative then you can very safely say that you know that that power function is going to be decreasing, similar to like the reciprocal function. Same thing goes for if you know that this power is a number between 0 and 1, then you can very safely say it will resemble something like the square root function in the upper in quadrant 1. One thing that I do want to point out that all of these functions have in common is they all share a key point of 1 comma k. And k is referring to the constant of variation. So if you have a function that is 2x to the, I don't know, 100th power, you can very easily say by this summary page that it would have a key point at 1 comma 2 because the formula says 1 comma k. Okay, so something that you can do without knowing what the parent function of x to the 6th looks like is you can guess what it would look like using the concepts on the previous slide. So I'm going to say, all right, g of x equals x to the 6th is a power function. And the power is a number greater than 1, right? The power is a number greater than 1. So this is going to resemble an x squared function, an x cubed function, etc., because it has that higher positive power. So I can kind of guess. I could even give you more information that if this is an even exponent, it's going to resemble other things with even exponents, like parabolas. So I could very safely say that g of x looks a lot like a parabola. So then what would f of x look like? F of x is negative 2x to the 6th. Okay, so I know that this negative is going to reflect the parabola I just drew over the x-axis. And I could also identify that key point. So the key point was at 1 comma k, and in this case, k is negative 2, so 1 comma negative 2 would be the location of that key point. You can kind of just make this your own thing. It's not the vertex, it's just a key point on the graph. So the function would also be a parabola, but flipped. Just pretend that doesn't look like garbage. Parabola but flipped, and it would go through that key point. All right. Last thing on this slide, or this lesson, is matching power functions to equations. So this would just be something that you would be able to do using those graphs from the last couple slides as like reference points. So let me split the screen and share so we can look at both at one time. There we go. So we have our equations on the left and our graphs on the right. We're going to match them up using the skills that we have applied and investigated from back here. Okay, so I'm going to start with something that I feel like stands out, and that's this negative exponent here, which, remember, negative exponents means that that thing could be in the bottom of a fraction. So I know that this is going to resemble a reciprocal function. And I also know that the negative 2 in the front is going to make it flip upside down. I could also take it further and say that I know a key characteristic point on this curve is going to be the point 1 comma k. So if I say 1 comma k, in this case it would be 1 comma negative 2. I'm just going to look for a graph that has a point at 1, negative 2. This guy down here does. So that's going to be our match. So this is graph C, and graph C is the same as equation 2. Maybe we'll just try that little key point trick for all the rest of them. So like number 4, this would be a number greater than 1, so it should resemble kind of an increasing function. But we do have a k value. So maybe we'll say, all right, what would be my key point? My key point would be 1 comma the k value, which is negative 1. So I'm going to look for a graph that has 1, negative 1. There it is right there. So this is graph number 4, which is the same as D. Okay, what about up here if I keep continuing with that 1 comma k key point thing. K is 3, so 1, 3 would be one of my key points. So it looks like we have a winner with graph A. And then the last one would have a point at 1, 1.2, because k is 1.2, which leaves us with graph B.